Okay, so one thing, let me go ahead and give this to you, just in case I get exceptionally boring or something. You guys have this to look at. It's a practice test. So I told you I was going to have this. So I'll have the answer key for this. I believe is the next. I test the next Wednesday, right? I think. So I'm going to have the answer key on Tuesday.
Does the practice test you said?
Is this it usually?
Huh?
2 pages?
One more?
No. What? No. I'm done. Shut up.
All right. I'll take a test for you.
Specifically her name.
But everything past what you give everyone else is extra credit. How about that?
Nope. But you're locked in for the other thing. So this, yeah, like I said, put it away unless we're talking about something you totally understand or something. On Tuesday next week it's going to be review day, so I'll have the answer key for that. Yay!
Yes, Maria. Talk you well.
We do what we must. If anyone comes looking for us, you have our back. Yeah. Okay.
Wait, Mark.
Yeah. You guys are going to get up on the board here in a bit.
It's your
The
turn.
whiteboard.
It's your turn. We really put Maria through it.
You guys are the tutors now.
I'm the tutor now. All right. First off, let me show you this. This is freaking cool as shit. So we're talking about parabolas, and one of the most cool immediate uses of parabolas, there are telescopes. Obviously, a lot of telescopes use lenses and so forth, but there are telescopes that use parabolic mirrors. Because the idea of a parabola is anything coming in will get reflected back. So normally the light hitting the surface anywhere on the surface of the parabola would come to a focal point. And do you see how the focal point would normally be back here somewhere? So they put a little mirror. This happens to be hyperbolic, excuse me. So all kinds of bolics happening. So we got parabolic mirror, hyperbolic secondary mirror. And that, instead of letting the focus go over here, it takes it back here. So then somebody can be here. So all this is in here. So you guys kind of with me. So it's basically. Now, a telescope that uses lenses is more like our eyeball, because our eyeball's got a lens. The light goes through the lens and then gets focused on our optic nerve and blah, 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 blah. Right? Of course, it's upside down, all kinds of weird shit happens. You don't hear there's not a lot of telescopes with mirrors because they get kind of difficult to construct that big, right? But it is really good. And notice also, do you realize that the middle would be missing light? The middle would be blank. There's like a blind spot in the middle. Okay. You also have things like this dude, which it's really difficult. Oh yeah, let me do this. All right, give me a second. This guy, it's really hard to make a parabolic mirror as big as we need it to be. So what they did instead was they have smaller mirrors that together mimic a large parabolic surface. And then here's your focal point, right? Okay, there's another one that gets even niftier. Where's that at, Jeff? Here it is. This one is liquid mercury at the bottom of this. And they spin it. And when you spin it, it tries to climb up the edges. So they have the edges tall enough so that rotation, they're spinning it on. So it climbs up the edges and it forms a parabola. So it's a mirror. When it's rotating, it's in the right shape. And then, of course, they've got the collector up here. So they spin it, it forms a parabola, in comes the light, gets focused on the focal point. Trippy. So anyway, I thought I'd share that with you because we're studying parabolas. So one thing is, why do we care about the formulas for parabolas? Because the formulas directly lead to, if I know ahead of time what shape I need, that influences variables, tells me what my equation needs to be. I don't know if you guys are with me or not. To make the parabola actually that shape that I need to do what I want it to do. Okay. nifty shit. Okay. Go over there. So let's do this. The last thing we did last time, I think, was we proved the quadratic formula. I don't think we did much beyond that. Is that true?
Yep.
Were you guys here? Okay. Did I hallucinate that? I'm hallucinating right now. If I am, then you guys could say anything to me. I wouldn't know. So we learned if I have an equation like this that I need to solve, we can then do this business. So then it just becomes a plug and chug situation. Okay, so one whiteboard down. I think, all right. Let's do this. I want you guys to try out, and everybody is everybody taking notes, potentially? What do you guys all have? You all have, did I give you, oh yeah, you all have the practice test. If you would, please. I'll give you 2 to try. Let me think ahead a little bit. Yeah, that'll work. That'll be nice. And then slightly trickier one. That'll work. Yeah, that'll work. That'll work beautifully. Cool. Yeah. Kick ass. Okay, good. I'm making sure that these do what I wanted to. So, what I want to have happen is 1, 2, 3, 4 groups. Somebody can use that, and then somebody can use this. I'll turn this off. Somebody can use this, and somebody can use that. Some groups. You with me? Maria has acquired some whiteboard markers. I'm assuming they're probably an array of colors. They're behind. Yes, they are an array of colors. Kick ass. So, one group will be, let's see, you guys here. Yes, so we got Anas, we got Danica, we got, why is your name escaping? Sierra. I know your last name is like ringing through my head. And then we've got Corinne, we got Mao, and we got Aubrey. You guys are a group, yes? Okay, so if you're a group, you might want to stake out whichever board you want and whichever color pen you want. Why don't I get Kendall, Kelvin, and Melissa, you guys work together. And then at least you guys. You guys love it. You guys work together. So those 4, let me turn this off. Does everybody have their problems written down? Everybody have their problems written down?
Yeah.
All right. Grab a marker, make sure it works. I have another purple one in case there's an issue.
You gotta make sure you put the coefficients in parentheses.
Yes.
The distribution of the data.
Yes. So basically, anytime you're substituting, you really should put it in parentheses to preserve what's happening. You with me? Did anybody notice a mistake you made and figure out why it was wrong? Anybody want to share? Huh? What's that? Why they looking at you?
When you said mistake, pointed at me.
Oh, sure. Anybody? Anybody?
I mean.
So one thing was the square root of -4 had a few people tripping out, and that's understandable. But when you have the square root, look at me writing on a freaking one. Square root of -4, you can always think of it as square root of 4 times square root of -1. Break it up. Just realize the really cool thing about negative roots, you're trained for them to not have an answer. So your immediate reaction should be, oh, I made a mistake, this can't be right. If the square root of 16 is 4, the square root of -16 is 4i. So all the negative inside does is just tack an I on. Because it literally is just an extra piece. You can factor it out, right? And that's just I. Yeah, I like it. So let me ask you this. what part of the quadratic formula made a complex answer? Which part of the quadratic formula would actually lead to a complex answer?
The square root.
Yeah, the stuff under the square root, correct? Okay. Let's see, what should I do? I don't want to get rid of this work, but I need to show you shit. Let's see. Maybe I can, yeah, you guys, this is small. I can write it right here. Okay. Right there. I'll just write right there. This piece right here, this guy, if you just analyze the output for that, if this is positive, what kind of answers will you get? Real. You'll get 2 real answers, yes? If this is negative, what kind of answers will you get? You're not going to believe it. Complex. And just really 2 complex answers, yes?
Yes.
And just real quick, imaginary is very specific. It talks about just the I piece, but these are complex because they have real and imaginary. So there's real, there's imaginary, and when I fuse the 2 together, then you have complex. Either through the earrings or the fusion dance. No, okay. And then finally, what's the one situation I left out that I didn't make an example of? Yeah, what happens if that was 0?
You would still get a real.
You get 1 real, 1 complex, maybe.
No, real.
Here's the neat thing. It is impossible to get one complex solution from a real valued equation. What I mean by that is the equation started off with only real numbers, correct? So if you have a real valued equation, you cannot get one complex solution. They will always show up in pairs. And you see why. It's got a plus or minus, so the minute this is negative, you're going to get 2. Yeah? Now, if it's equal to 0, do you all agree it will be real, because the only time you get complex is if inside the root is negative.
Yeah.
If it's 0, it's fine. But then you get the plus or minus is gone. So you get 1 answer. So can we construct an equation where that would be true?
Probably.
Probably. I don't know. Maybe we could do it. So let's see. Let's see if Jeff can do it.
I believe in you, Jeff.
Oh,
Can we do another two?
we'll see what's misplaced. Okay. So what I want to do is I want to make a quadratic equation. So what about this one here? Can you guys go ahead and try to do the quadratic? Actually, yeah, do the quadratic formula for that. Yeah, you go for it. You're there. Go for it.
Yeah, I mean, Maria said I have to stand here the whole class. So.
Well, it's good to know you have to do what she says. This is perfect.
Nobody quote him.
That's hilarious. So Damien does what his hallucinations tell him to do. That's good to know.
What am I, what?
Hallucinations.
She literally said I can stand here all the whole
Is that-
class.
Yeah, I didn't hear that.
We had the camera rolling, no, we can check.
It is hearsay. Yeah, it's hearsay in the sense of he heard it, you said it.
See what I'm saying, bro? He gets it.
Oh, man.
Got a jury.
Apparently. This is ethics and law class. So let's see, negative b plus or minus square root, bare square, minus 4ac. So you guys see what's happening here?
Yeah.
Over 2a. So you get 6 plus or minus square root of 0 over 2 is 3. Because this is 6 over 2. Now real quick, why does anyone see from the beginning a better way to solve the equation than quadratic formula? And does this, real quick, remember fundamental theorem of algebra? Anybody remember the fundamental theorem of algebra? What's the highest degree in this formula, in this equation?
2.
2. So I expect 2 answers. How many answers does it look like we got?
One.
Shit. We have just disproven algebra. Back it up, kids. No. What's the better way to solve this? Can you factor this?
Yes.
Yeah, so factoring is always better than quadratic. How do you factor this?
X plus or minus.
No.
Two negative.
Two negatives. They have to be both the same sign, and they have to both be negative, and then 3. Do you see how I get 3 twice?
Yes.
Okay, that is the situation that will end up with b squared minus 4ac being 0. Is if it's something that would have factored like something squared, so you get the same number twice. That's why this gives me one number, but I still have 2 answers. They just happen to both be 3. Okay, maybe, okay.
So that would be like the vertex on 3, right?
Yeah, that would be the vertex sitting on the x-axis. So one thing we haven't gotten to yet is fully looking at the graph of this and how does the equation affect where the parabola is.
So we shifted the parabola right 3.
In that case, it would shift right 3. Kick ass. So real quick, let's see if you guys cool it. You got 2 answers on the first one, right? That's a parabola that would hit the x-axis in 2 places. In fact, they should both be positive, Jeff, but someday I'll wake up enough. Okay, here we go. Rah! So there's 1/4, there's 4. So that, when you get 2 real answers, the parabola hits the x-axis in 2 places. Why did I draw it up? Does anyone know that? We haven't talked about it officially, but how do I know this opens up? Does anyone know? Because some parabolas open down.
It's positive.
If the first coefficient is positive, it'll open up. It's kind of related to slope, but it's squared, and that's why it kind of goes up in both directions, yes? If the first number was negative, it would open down. It would be saying. This one got 2 imaginary solutions, yes? If it hits the x-axis, those are 2 answers, 2 real numbers. You didn't get any real number answers here, therefore the picture should never touch the x-axis. It can't hit the x-axis. Do y'all agree with me that these are answers because they make the output 0? If you're on the x-axis, doesn't that make the output 0? Because I'm not up or down, I'm right at 0, yes? This one had no real answers. Therefore, the parabola either has to look like this or like that. It can't touch the x-axis. We happen to know it's this one because, again, this one opens up. Now, of course, I'd have to do a little more work to figure out, is it over there? Is it over there? Okay. Is it all with me? Go ahead.
Just explain it again, but slower about the x-axis thing and why it can't hit it.
If it does hit the x-axis, can you tell me what the output is here? What's the value of y here? 0. That's why it matches with the equation. I want the output to be 0, correct?
Yeah.
Where do I have to go so the output is 0? X-axis. If I'm not on the x-axis, the output is more or less than 0. Yes?
Okay.
Does that make sense?
Yes.
If I want y to be 0, if I want the output to be 0, I must be on the x-axis.
Right.
So if I hit the x-axis, that's an answer to this equaling 0.
Okay.
This is what this looks like because it had 2 real answers, therefore it must actually hit the real x-axis.
Okay.
This one did not have any real solutions. You only got complex answers. So it cannot hit the x-axis. If it did hit the x-axis, I should have gotten some real answers, specifically where I hit the x-axis. If I have a parabola that actually hits the x-axis, once or twice, that has to be the real solutions. Did we have any real solutions on this one?
No,
Therefore, it cannot hit the x-axis.
I believe you.
Okay.
I just don't understand.
If it hits the x-axis, what do these real inputs do?
I mean, I understand. I get that part. What I'm not understanding, I don't think, is that the quadratic equation is solving ax squared minus bx minus c equals
X squared plus
0.
bx plus c equals 0, yes.
Right.
Which, if I set something, a function equal to 0, that's the same thing as saying finding the x-intercepts.
Okay.
Because what did we make 0? We made y 0. Yes.
Which makes sense to me.
So if I get real answers, I have real x-intercepts.
Okay,
If I don't get any real answers, I don't have any real x-intercepts.
but it's a complex number. It
Total.
involves a real number. And
It's
so-
part of it is real number. So remember when the guy picked that picture up in the video we watched?
Yes.
Stay with me, guys. Stay with me. Stay with me.
I don't think so.
I don't think I should.
Yeah, I don't think
Oh,
I
shit.
remember you explaining it sort of, but I
Oh
don't.
yeah, darn it.
But,
Alright,
but
I might have to post that in Canvas before I forget, so watch. There, okay, the imaginary axis is over here, yes? Not a T, Jeff. You with me?
okay.
Yes? Because if you multiply by a full -1, but if you multiply by half of a -1, that's why the square root of -1 is I. So is everybody with me? I love it. So you guys look at me like, just keep going. Okay. You have a real number line. To the side of it, you have the imaginary axis. A really bad name. Poor choice, but that's what we call it. This is what this would look like if I graphed it, roughly.
Do you guys want to come up there and?
Sure. I'm curious.
Fucking old kids. So you're saying that this is. Do you mind if I-
Do whatever.
Okay. So you're.
Erase my picture.
Okay, whatever. So y-axis, x-axis, imaginary axis.
Sort of.
Sort of.
Well, in this case, it's more like, so here guys, you know this is X and this is Y?
Uh-huh.
Z.
Okay, so.
Now, you could think of this as the imaginary axis is here.
Right.
And that's why when, in the video, the guy picks the picture up and there's all these colors that represent the imaginary numbers.
So for artistic expression's sake, imaginary axis.
Sure.
So you're saying that even though this involves, because what we're saying when we're saying x equal, we're saying that when y equals 0.
All right, listen. This is perfect. You'll get this, okay?
Okay.
So it's very cool with the fact that imaginary numbers live on the sides of axes. So when I graph this, it's like I'm taking the x-axis and turning it. So now I'm turning it back. Have you guys ever seen this, like the 3D? Are you guys with me? So that actually is kind of like going into the board. Are you guys at all with me?
Yeah.
Okay. This right here means the real part is -3/2, but the imaginary part is I over 2. So I'm going to go out I over 2.
Right.
So when we graph just this slice, the real slice, I'm not going to see where it hits the x-axis. If we graph the imaginary part also, then I could see where it hits the x-axis. It hits the x-axis in an imaginary,
Dimension.
yes.
Okay.
It
So
gets trippy. It gets trippy. So let's just stick with real stuff. If I don't get any real solutions, that means the parabola this represents would not hit the x-axis in a real.
because
Slice.
we're only graphing x and y and not.
We're only graphing the slice that's fully real.
Got it.
Yeah.
Thanks.
I'm really sorry. You guys, no, it's really good. I don't mean to say that, but things get a little weird. I don't want you to feel like you're gonna have to do a lot with imaginary numbers. You're not gonna have to
No, they're just.
actually lift.
The
Alright.
fabric of reality.
Trying to go back to where I was. Yes.
So we have real numbers, imaginary numbers, and complex numbers, right?
Yes.
3 groups, or do we have more?
Well, complex is if you mix real with imaginary.
It's like a Venn diagram.
Okay.
Yeah.
So just 3 groups.
So this is an imaginary number. This is a real number. This is a complex number. Now the really pedantic, this is a complex number, this is a complex number, this is a complex number, because this is 0 plus 3i, this is 4 plus 0i. So if you could put it in the form a plus bi, it's complex. But we would say this is purely imaginary, this is purely real, that's complex.
Is there a fourth group of numbers?
Dude,
Is there?
depends on what you want to do with stuff. So, yes.
I'm gonna invent a fourth group of numbers.
Those are the main ones.
So fractions are real numbers?
Fractions are real numbers, yeah. Anything you can find on the number line is real. And 1/2 is between 0 and 1, blah, blah, blah. You can find square root of 7, that's real, right? Or square root of -1, not on this number line, it's adjacent. Okay. Is that cool? It's to the side. Yeah, you guys need to watch that video. Yeah, so I need to post that for you guys.
I say we just watch it again.
No.
Okay.
So somebody that went directions that were cool, but I don't want anyone to feel.
No, it makes more sense now, actually, weirdly.
Yeah, when you get one solution, that's when, like you said, it just touches, it just sits on it. Yes. So it's kind of neat if you have a parabola and you're able to like affect the equation, you can kind of make it go up. So it might have two solutions, and then it's got one solution, and then it's got no real solutions if you lift it up high enough. Okay, I like it. Okay, so I'm going to transition back here. So I really don't like the whiteboard. I'm going to erase this. I'm sorry. I've got that one. I've got for posterity. Is that there?
All of them? No.
Let's start the first
Oh, no.
Band-Aid. Band-Aid time. Okay.
Want me to erase this one?
Sorry?
Want me to erase this one too?
Not yet. I haven't recorded those yet.
my name tag also?
Yes. Can you bring the, I can't leave this corner.
Make sure she pays you. Okay. So the thing I want to focus on tonight that's new. Let's see, which part do I want to do? Yes. Okay. Beautiful. I want to kind of lay down some groundwork for a really nifty idea. Can you guys remind me the name of this point here?
Vertex.
Yes. The vertex happens to be for a quadratic function, the location of either the absolute min. Is that cool? Y'all agree that would be an absolute min?
Yeah.
Or the absolute max.
Wait,
What's that? Go ahead.
Wouldn't the absolute max be, well, I guess, based off that graph, it'd be the highest point?
That's why I was saying if it's quadratic. If it's higher powers, it could turn multiple times. And then you could have this one, but then later you get higher. And then later you get higher, yes? Okay. Is that all right? I think that's what you're thinking about.
Yeah.
But if it's quadratic, it's only got one turning point. So it's either the top or the bottom. Okay. It'd be great if we had a shortcut way to figure out the vertex of a parabola that we're given. So if I'm given this parabola, I want a nice, quick way to figure out its vertex. Yes? Why is that good? Because the vertex is really important. If I keep going back to this because it's standard. If I have a profit function, I want to know the vertex because that gives me a target. That's the highest profit we can make given the parameters of our business that feed into this equation. I'm like, now let's find what our max profit is and let's work towards that. And every day it kind of shifts a little bit based on stuff, but are you guys at all with me? And I'm not, that's one reason why I'm not in business, I'm driving crazy. Chasing that profit. All right. So let's talk about this. Can you guys, on this admittedly kind of crappy picture here, these two are the x-intercepts, correct?
Yeah.
Yes.
Where must the vertex be?
In between them.
Because what's true about a parabola, it has symmetry, yes? Right down the middle is the mirror, yes? So if I have two things across from each other, the intercepts in this case, the vertex has to be right in the middle of them. Are you guys with me? If I have something that looks like a parabola, but it's part of a higher order degree thing, it doesn't have to do that because then it might not be perfectly symmetric. But if it's quadratic, it's perfectly symmetric. So if I could find the intercepts, then between them is the vertex. So let's do this. Let me start off with a nice one. Just to lure you guys in. Let me see. Okay. Can you guys find the x-intercepts of that? So when I ask you to do something like that, you start to translate what I just said. How do I get the x-intercepts? I make
Make it equal to 0.
Make what equal to 0?
The quadratic.
Y. Which thing up here is Y?
F of X.
So you put a 0 here, and then you solve it. Yes? So that's a huge part of mathematics is you have an instruction, you got to translate what the hell that instruction is telling you to do. Are you good? Instruction? Okay. So please don't use quadratic formulas. No need to, right? So if you set this equal to 0, what can you do with this? What do you get? So where are my intercepts?
4, 2.
2, 0.
We do this x-intercepts, 2, 0, and 4, 0. You guys good?
Yeah.
Alright, can you guys make a semi-decent graph? I negative stuff too. Let's see if I, oh God, what have I done to myself? We'll find out. Alright. My intercepts are 2, 0, and 4, 0. So what must be the x piece of my vertex? 3. Do you guys see that? That sets up the mirror. The mirror has to be directly between them because one point is the reflection of the other point. You can think of it that way. So the mirror must be right in the middle. How do I find where the vertex is then? Yeah, we know. No. We know that the x is 3. How do you get the y?
Oh, you plug it in.
Plug it in. We know the function, don't we? So, I really want everybody with me. If I have a way to get the intercepts, and I get them, now it's easy that the x piece of the vertex must be between those two. Then how do I get the y? The same way we always do. Try to take over the, no, we plug it in. So f of 3 is 3 squared minus 6 times 3 plus 8. What do you get? 9 minus 18 is? Negative 9 plus 8 is? Negative 1. So 3, negative 1. Look at you, Jeff. You did good. Thanks, Jeff. And then there's my parabola. Whee! Whee! You can go one step further, although it wouldn't really fit on my graph. How do you find the y-intercept? Make x 0, so what's the y-intercept? 0, 8. And then if you made your scale good enough, you can plot that point. How are you guys feeling? Can you always find the x-intercepts that easily? Didn't I make it really nice? In fact, look what I did. Not only was that easy to factor, frickin' 3 is right between 2 and 4. So what if the x-intercepts was 7 8s and 9 11s?
You can still do it.
You can still do it, but would you want to? No. I'm sorry. You had a little bit of a, no, I didn't play it one. You could totally do it.
I deserve that.
You got that?
You could totally do that.
Okay. Gabby was doing smaller. Okay. So here's the ultimate cool part. Yes.
Well, how do you find the vertex if it's an imaginary?
You ready? Okay. How do I find the x-intercepts in a situation like, for example, the situation like what we had? How would I find the x-intercepts this thing here? Please tell me that doesn't work. Does that work? No. How would I solve this? That's finding the x-intercepts. You all agree? How would I solve this? You're a little bit ahead of where I want to be, which is beautiful. Sit there for a second.
Do you add 3?
Come on. What do you, when you can't factor something?
Oh, you're just doing
Quadratic formula, right? So just to really hammer this home, what is the quadratic formula's job? The quadratic formula's job is to solve something like this, correct? So let's translate that further. What do I get if I solve this? I get the what of the graph? The x-intercept. So what does the quadratic equation do? Quadratic formula gives us the x-intercepts. Okay. So forget this guy. You've done your job. What is the quadratic formula? It's this business here, right? Now watch, stay with me. This gets a little trippy. I'm gonna rewrite this a little bit. In fact, I'm gonna take one step back from the time we proved this. So I'm gonna write this way. Is that cool? That over that, plus or minus that over that. And just split the fractions apart.
Yeah.
Now, think about this. Here's negative b over 2a, yes?
Yeah.
Don't I add this to it to find one x-intercept? And don't I subtract this from it to find the other one?
Yes.
What did we just say is going to be directly between the two x-intercepts?
Negative A.
The x piece of the vertex. Even if these things are imaginary. Even if they're imaginary, it's still symmetric. Okay. So it's going to be right in the middle. So this is the ultimate shortcut to finding the x piece of the vertex. If I am given something in this form, and my only thing I have to do is find the vertex, then freaking do this. Now what does that do for me again? Finds the x piece of the vertex. And then of course, how do I find the y piece? Freaking plug this shit in. Yes.
You like plug it in.
It's totally right. Why wouldn't you? Of course you plug it in. All right. So,
I can do it.
that's trouble with me if I do that. Okay. Has anybody ever seen that before? The shortcut for finding the vertex?
Yes.
I've seen it,
Yeah?
but not why.
In calculus, you guys actually prove that in different ways. One of the first things I like to do, in fact, I'm going to do it in my class next time. I'm going to show them using calculus to reprove this. Well, we don't need calculus, do we? Screw calculus. We got it. Whatever, calculus. All right. So real quick, can you find this guy's vertex? What do you got, Jeff? I don't know, Jeff. Sure. I just want that guy's vertex.
All right.
What? As you guys are doing, I'm gonna record all these for posterity. Oh, that's just me. Who cares? Damien, calm down, Damien.
What's up? What's up? Hey guys, whoever was absent today or whoever is watching this.
Give a
video,
shout out to my YouTube channel. Come on.
What is it? I am.
My views are going down, Damien. Come on.
No.
How's everybody? Hey.
Retention rate is just plummeted as soon as you showed me on the screen.
My social blade, my analytics. Oh my God. I've gone from 0 to 0 per month. Oh shit.
Those monetization.
Did I just get it demonetized?
No. No. I'm not sure on YouTube. I'm not even sure what.
I should have started singing a song so I get you copyrighted.
Oh yeah, it's true. I did get a copyright strike once because I accidentally recorded that video I showed you guys.
Oh, yeah.
One time, it's a while back, so now I'm really careful to turn the damn thing off.
I'm gonna start singing in class one time so I can get you started.
I'm sorry guys, I don't mean to be distracted. What's the shortcut for the vertex? Yeah, so then you identify B and A the same way as if you're doing quadratic formula, but you don't have to do the whole quadratic formula, that's awesome. So what's B? Negative 24. And what's A? 6. So now we catch up with Kelvin back there, we get 2.
Yeah.
So that's the X piece of our vertex. How do we get the Y piece? That's insane. 6 times 4 minus 24 times 2 plus 11. 24 minus 48 is negative 24 plus 11 is negative 13. So then my vertex is at 2, negative 13. It's pretty good, right? It's pretty good. Not bad. It's pretty good.
It's all right.
It's like fine.
I mean, I guess.
For what it is, I mean,
I guess.
whatever. Do I have to know that, Mr. Waller? All right, stop. I don't want to do that yet. Yeah, I want to stop early tonight. Yeah, we're good. We're actually very much on track right now. Because the next thing we're going to do is what you alluded to, Kelvin, and that's putting quadratic equation, a quadratic function into vertex one. Whatever the hell that is. And it's going to relate to transformation somehow, which is everybody's favorite. So, let's officially end. If you have any issues with me ending early, just go see my dean.
I won't be